Okay, so we're talking about OpenStax statistics. We're in chapter 6, and I'm in the class Excel file. I'm on tab 6. So we're going to be talking about using the normal distribution to approximate the binomial distribution. Oh boy. So you can access the text for free. You can look in the description of this video and you can get a link to the textbook. The workbook that I'm going to work out of here is free at divideandconquermath.com. Just go to the OpenStax statistics section and you can get all of this good stuff. Just as a note, so at the time of making this video, so the material that I'm talking about here is discussed in the OpenStax business statistics text, but not in the regular statistics text. But I think that this topic in particular, it's very important to understand because it's kind of the foundation for confidence intervals and hypothesis testing with proportions. So I have supplemented this material into my regular statistics course. So if you are looking for notes that kind of combine the OpenStax statistics with this material, you can also get my PowerPoint slides for free at divideandconquermath.com. Okay, so the situation is this kind of an odd situation, but we need something to kind of anchor this to. So imagine that it is known that only 10% of Australian Shepherd puppies are born with what is called perfect symmetry in their three colors, so black, white, and copper. So perfect symmetry is defined as equal coverage on all parts of the dog when looked at in the face and measuring left and right down the center line. So a kennel would have a good reputation for breeding these dogs if they had a high percentage of dogs with this criterion. So during the past 5 years, and out of 100 dogs born to Dundee kennels, 16 were born with this specific coloring characteristic. So the question is, what is the probability that out of 100 births, more than 16 would have this characteristic? Okay, so this example it's kind of cool on a few levels, honestly. So first of all, this is like one of those things where somebody gives you a piece of information and like you might hear it and then you might say, whoa, that's really impressive. But the thing is that statistics is what actually tells you, is it impressive or is it not? Because what makes something impressive from a statistical standpoint is that you have like kind of that probability to back it up, right? So first of all, this situation is really utilizing the binomial distribution. So the binomial distribution is based on the idea that you have discrete data, so that's countable data. And then the idea is that you have characteristics, so it's like a binary characteristic, so yes or no. In this case, it would be perfect symmetry or not perfect symmetry, true or false, black or white. So for a binomial distribution problem, you need to have something where it's like a clear, yes or no, 0 or 1, whatever. And you need to know the probability of that. So in this case, we know that there is only a 10% probability of having this perfect symmetry. So that is what we are going to call our success. So I'm going to label the information that I've been given up here. So my P is going to be my success. That's going to be 0.1. And what we're interested in is out of 100 dogs, what is the probability that more than 16 would have this characteristic? So we're talking about 100 dogs, so that's going to be our N. And then the last piece of information that we want to get out here is a Q. So Q is always going to be 1 minus P. So you can see how I've set this up here. So just 1 minus what my P is. Okay, so this is kind of our baseline information. Okay, so with the binomial distribution, since it's discrete, one of the things that can be kind of rough about it is asking a question like this. So in 100 births, what is the probability that more than 16 would have this characteristic? This requires you to calculate all of the probabilities from 0 to 100. And that's what I've done over here. So I just wanted to like set this up and show you guys kind of what's going on. So I have this binomial distribution table where each x is the outcome that we're interested in. So x equals 0, that would mean the probability that out of 100 births, there are 0 puppies that have this perfect symmetry. X equals 7, this is the probability that out of 100 births, 7 puppies have this distribution. So to really answer this question, of 16 or more that have this characteristic, you have to calculate all of the probabilities from 0 all the way down. So I'm going to keep scrolling down to 100. That is really the way to answer this question when we're talking about the binomial distribution. So the good news is this is easy to do with Excel because there is a binomial distribution formula. In this case, I've got a prompt here just to kind of show you what it is. So I've got my binomial distribution, whatever my X value is. The prompt is the total number of trials, that would be 100, the probability of success. And then when you have a binomial distribution formula, you always just put a false here. It's just how that works for that particular formula. So if you click on one of these binomial distribution formulas, you'll see how I have this set up. So I'm referencing my X, and then I'm referencing the number of trials, that was 100, and the probability of success, and then I have the false here. And so the nice thing is, once I set this up, so you can see then this formula is something that can just be dragged all the way down. So the good news is it's easy enough to set this up with Excel. And so then when you ask the question, what is the probability that in 100 bursts more than 16 would have this characteristic? So that's going to be the probability that X is greater than 16. So I can just come down here. So it's more than 16. So 16 is not included. So really, I would just sum up everything from 17 all the way down. So to answer this question, so if I want to get this probability as X is greater than 16, I'm just going to sum up all of these probabilities. And so I get 0.020599. So going back to that question of, is it actually impressive that a kennel got 16 puppies with this coloring characteristic? There is a 2% chance that a kennel could get 16 or more than 16 dogs within a group of 100 with that characteristic. So that is pretty rare, okay? So as you can see, using the binomial distribution, it can be kind of a lot of work in some ways if you have a lot of trials. So in this case, we had 100 trials, so we had to set up this giant table to make this work. And so the idea here is that in some cases, instead of having to do all of this work for the binomial distribution, instead what we could do is we could actually use the normal distribution. So this is going to be a little bit different in how we set this up. So for the normal distribution, I have the same information. My n is still 100, my p is still 0.1, my q is 0.9. Now, one thing that we get interested in, you aren't allowed to use this unless n times p and n times q are greater than 5. So you can see I started here, n times p is 10, and then if I just check, so n times q is 90. So as long as both of these numbers are greater than 5, you are allowed to use the normal distribution to approximate the binomial distribution. So this is just a check for us. We're good to go. So from here, the next thing that you need to know is you have to calculate your own mean and standard deviation. Now, when we are specifically referring to the binomial distribution, things that are in the binomial distribution have their own way of calculating a mean and a standard deviation. The mean is calculated just n times p. So we are actually already calculated n times p, right? That was already done up here. And then to find the standard deviation, that's the square root of n times p times q. So I take the square root of n times p times q. That's going to be my standard deviation. So now when I'm using my normal distribution, these two numbers here, this is the mean and standard deviation that I want to refer to in this case. Okay, so from here, we can really just treat this like the normal distribution. So we're going to calculate the probability that x is greater than 16 using the normal distribution, which means that I need to set up my, graph first, right? So the first challenge I have to you is you've got your mean, you've got your standard deviation, you know that you want to find the probability that x is greater than 16. Can you draw what this situation should look like using the normal distribution? So maybe pause here and give that a try, hit play when you're ready. Okay, so here is now this information translated into the normal distribution. So we said that the mean is 10, so this normal distribution is centered at 10, and we want to find the probability that x is greater than 16. So here's where 16 would be relative to 10. So this area here is what I want to find. So the beauty of this is instead of having to do all of the work that we just did with this binomial distribution, which is kind of a lot of work to do, I can just go back to using my normal distribution formula. So I'm going to find now that probability that x is greater than 16. I'm just going to use my norm.dist function. So 16 is my x, 10 is my mean, 3 is my standard deviation, and then when you're talking about the norm.dist function, it's always true at the end. Okay, so remember, this is always returning a number to the left, so I can tell just by looking at this that this number is clearly not this little sliver in here, so I can see here I was supposed to take 1 minus that calculation. So this comes out to 0.02275. Okay, and so this is kind of the whole point then of doing this calculation. So let's compare these two. So from the normal distribution versus the binomial distribution, so I calculated the probability in each of these cases. And if you round both of these to just kind of that nearest like first percentage, this comes out to 2% and this comes out to also 2%, right? So this is kind of that beauty of being able to use the normal distribution instead of the binomial distribution. There are certain questions where instead of having to do all of this work with the binomial distribution, as long as you meet these two criteria, that your n times p and your n times q are greater than 5, you can then just compute your mean, your standard deviation, and then rather than having to do all of this, you can just use the normal distribution, which I would argue is a lot easier to use than going through and having to set up this whole giant table like we did here on the left. So that's the idea behind the binomial distribution versus the normal distribution.